Welcome to this problem walkthrough. In this session, we'll tackle an exciting problem, number 11, container with most water. This classic algorithm problem is a favorite in technical interviews and challenges you to think about efficient solutions for optimizing areas. Let's dive in. In this problem, we are working with an array of integers called height, where each value represents the height of a vertical line drawn at a specific x-coordinate. The task is to identify two of these lines that, along with the x-axis, form a container capable of holding the most water. The amount of water the container can hold depends on two factors: the shorter of the two lines chosen and the horizontal distance between these two lines. Importantly, the container must be upright, meaning the lines cannot be slanted. The goal is to calculate and return the maximum area of water that any such container can store. For example, consider the input array height equals 186254837. Here, the two lines that form the optimal container are located at indices 1 and 8, with heights of 8 and 7 respectively. The distance between these two lines is 8 to 1, which equals 7. Since the shorter of the two lines has a height of 7, the area of this container is calculated as 7 multiplied by 7, giving us a result of 49. This is the maximum amount of water that can be stored using any two lines in this array. Now, let's look at a simpler example with the input height equals 1 to 1. In this case, there are only two lines, so they automatically form the container. The distance between these two lines is 1 to 0, which equals 1. Since both lines have a height of 1, the area of the container is 1 multiplied by 1, resulting in 1. This is the maximum water that can be stored for this input. Another example would be height equals 43214. In this case, the optimal container is formed by the lines at indices 0 and 4, both of which have a height of 4. The distance between these two lines is 4 to 0, which equals 4. The area of the container is therefore 4 multiplied by 4, which equals 16. This is the maximum amount of water stored for this input. Finally, there are some constraints and edge cases to keep in mind. The length of the height array, denoted by n, must be at least 2 and can go up to 100,000. Each height value is non-negative and can go up to 10,000. Edge cases include arrays with the minimum size, arrays where all heights are 0, arrays with uniform heights, and arrays with highly varying heights. Additionally, the algorithm must handle very large input sizes efficiently, ensuring it remains optimal even when n is at its maximum limit. To start, let's consider the brute force approach. The main idea here is to evaluate all possible pairs of lines to find the container that holds the most water. For any two lines at indices I and j, the area of the container is determined by two factors: the width, which is the horizontal distance between the two lines calculated as ji, and the height, which is the smaller of the two line heights, given by min, height I, height j. Using this, we can compute the area for every pair of lines and keep track of the maximum area we encountered during this process. The algorithm involves initializing a variable max_area to 0 and iterating over the height array with two nested loops. The outer loop fixes one line at index I, and the inner loop tests all possible second lines at index j where j greater than I. For each pair, we calculate the area, compare it with max_area, and update max_area if the current area is larger. Once all pairs have been evaluated, we return the maximum area. However, this approach has a major drawback in terms of efficiency, as it requires evaluating all combinations of lines, resulting in a time complexity of n squared. While the space complexity is minimal at 1, the brute force approach becomes computationally expensive as the input size grows, making it impractical for large arrays. The brute force approach, while straightforward, has significant performance limitations. Specifically, its n squared time complexity makes it infeasible for large inputs, such as when the array size approaches 10 to the power of 5. This motivates the need for a more efficient solution, which leads us to the two-pointer technique. The two-pointer approach leverages an important insight: the width of the container decreases as the pointers move closer together, so to maximize the area, we need to strategically manage both the width and the height. Initially, we start with the widest possible container by placing the two pointers at the ends of the array. Then, to maximize the height, we prioritize moving the shorter of the two lines inward. This is because the height of the container is limited by the shorter line, and moving it inward gives a chance to find a taller line that might result in a larger area. In contrast, moving the taller line inward does not address this limitation and is less likely to improve the area. This insight allows us to systematically narrow down the search space while still considering all potential solutions, making the two-pointer approach both efficient and effective. The two-pointer algorithm is implemented as follows. First, we initialize 2 pointers, left at the start of the array and right at the end. We also initialize a variable max_area to 0 to store the maximum area encountered. While the left pointer is less than the right pointer, we calculate the area of the container formed by the lines at the left and right indices. The area is given by the width, which is right left, multiplied by the height, which is the smaller of height left and height right. If this calculated area is greater than max_area, we update max_area. Next, we move the pointer corresponding to the shorter line inward since this gives the best chance of finding a taller line to potentially increase the area. Specifically, if height, left, is less than height, right, we increment the left pointer, otherwise, we decrement the right pointer. This process continues until the 2 pointers meet. By iterating through the array in this way, we ensure that each element is processed at most once, resulting in a time complexity of O(n). The space complexity remains O(1) since no additional data structures are used. This approach is not only significantly faster than the brute force method but also simple to implement and highly effective for solving this problem. When comparing the brute force and two-pointer approaches, the two-pointer method clearly stands out in terms of efficiency. The brute force approach requires O(n)² time, which becomes impractical for large inputs, while the two-pointer technique reduces this to O(n), making it scalable and well-suited for larger arrays. Additionally, while the brute force method is conceptually simple, the two-pointer approach is equally straightforward and leverages a clever insight specific to the problem, making it an elegant solution. The decision to choose the two-pointer approach comes down to its balance of simplicity, efficiency, and scalability. It systematically narrows the search space without missing any potential solutions, ensuring we achieve the optimal result. In conclusion, by adopting the two-pointer technique, we solve the container with most water problem in an efficient and clear manner, achieving linear time complexity while maintaining the clarity of the solution. This makes it the ideal choice for tackling this challenge effectively. The problem we are solving is to determine the maximum area of water that can be contained between two vertical lines on a 2D plane. These vertical lines are represented by an array of integers, where each integer corresponds to the height of a line at a specific index. The area between any two lines depends on the shorter of the two heights and the horizontal distance between them. To solve this, we start by considering a brute force approach. This involves evaluating all possible pairs of lines, calculating the area for each pair, and keeping track of the maximum area found. While this approach is straightforward, it is computationally expensive due to the need to examine every combination of lines, which we will explore in detail next. To implement the brute force approach, we begin by initializing a variable, max_area, to 0. This will store the largest area we've found so far. Next, we use two nested loops to iterate through all pairs of lines. The outer loop runs from the first line to the second to last line, and the inner loop starts from the line after the current outer loop line and goes to the last line. For each pair of lines at indices I and j, we calculate the width as the difference between the indices, j, I, and the height as the smaller of the two line heights, min, a_i, a_j. Multiplying these gives the area, and if this area is greater than the current max_area, we update max_area. Once all pairs are evaluated, we return max_area as the result. However, this approach has a time complexity of O(n)² due to the nested loops, making it inefficient for large inputs. It uses O(1) space, as no additional data structures are required. To address the inefficiency of the brute force approach, we can use the optimized two-pointer technique, which reduces the time complexity to O(n). The idea is to maximize the area by strategically moving two pointers, one starting at the beginning of the array and the other at the end. We initialize max_area to 0, then calculate the area between the lines at the pointers. The width is simply the distance between the pointers, and the height is determined by the shorter of the two lines. After calculating the area, we update max_area if the new area is larger. To decide which pointer to move, we shift the one corresponding to the shorter line, because the shorter line is the limiting factor for the height. By moving inward, we aim to find combinations with greater heights or widths. This process continues until the pointers meet, ensuring all potential maximum areas are explored efficiently. The two-pointer approach is significantly more efficient, with a time complexity of O(n), as each pointer is moved at most once. It also has a space complexity of O(1), as it requires no additional memory beyond the pointers and a variable to store the maximum area. Comparing the brute force and two-pointer methods highlights the power of optimization. While brute force evaluates all pairs, leading to O(n²) computations, the two-pointer technique focuses only on the most promising combinations by dynamically adjusting the pointers. The reasoning behind moving the pointer for the shorter line is key, since the shorter line limits the height. Shifting it is the only way to potentially improve the area. This optimization minimizes unnecessary calculations while ensuring that no possible maximum area is missed. The data structures used in this problem are minimal. The input array of heights is directly utilized to calculate the areas, and only two pointers, left and right, are needed to track the bounds of the container being evaluated. The algorithm handles edge cases gracefully. For example, if there's only one line, the area is 0, as at least two lines are required to form a container. When all heights are equal, the algorithm calculates the areas normally, as the relative positions of the lines still determine the width. For large input sizes, the two-pointer approach ensures efficient processing, making it suitable for arrays with up to 100,000 elements. If the array is empty, the function simply returns 0 immediately, as no container can exist without any lines. This robustness ensures the algorithm works effectively across a wide range of scenarios. This implementation solves the problem of finding the maximum area of water that can be contained between two vertical lines using the two-pointer approach, which is both efficient and intuitive. Explanation. 1. Initialization. Two pointers, left and right, are initialized at the start and end of the array height respectively. These represent the two lines being considered for calculating the water area. A variable max_area is initialized to 0 to keep track of the maximum water area encountered so far. 2. Iterative process. The algorithm uses a while loop to iterate until the two pointers meet. This ensures that all potential line pairs are considered. For each pair of lines, the distance between the two pointers, right-left, is calculated. The height of the water level is determined by the shorter line between height, left, and height, right. The area is then computed as distance *min, height, left, height, right. If the computed area exceeds max_area, it updates max_area to hold the new maximum. 3. Pointer movement. To maximize the area, the algorithm moves the pointer pointing to the shorter line inward. This is because moving the shorter line has the potential to increase the height of the water level in subsequent iterations. If the taller line is moved, the water level cannot increase. If height, left, height, right, the left pointer is increment, otherwise, the right pointer is decrement. 4. Termination. The loop terminates when the two pointers meet, meaning all possible line pairs have been evaluated. Finally, the function returns max_area, which holds the largest area found. Complexity analysis. Time complexity, O(n), where n is the length of the input list. Each element is checked at most once as the pointers move inward. Space complexity, O(1), as no additional data structures are used. This approach is optimal for the problem and ensures a fast solution even for large input sizes. This is the Java implementation for LeetCode problem number 11, container with most water. The solution mirrors the two-pointer approach used in the Python implementation. The maxArea method initializes two pointers at the start and end of the array and calculates the container area as they converge. Key differences include explicit type declarations and usage of Java's math.min and math.max methods for calculations. This implementation ensures optimal performance with O(n) time complexity. To solve this problem, we use a two-pointer approach. Initially, the left pointer starts at index 0, pointing to the first height, which is 1, and the right pointer starts at index 8, pointing to the last height, which is 7. the max underscore area is initialized to 0. In the first step, we calculate the width as the distance between the 2 pointers, which is 8. The height is determined by the shorter of the 2 heights, in this case, min, 1, 7, which is 1. Multiplying the width and height gives a current underscore area of 8. This becomes the new max underscore area since it is greater than 0. Since the height at the left pointer is smaller, we move it inward by incrementing it to index 1. In the next step, the width decreases to 7, and the height becomes min, 8, 7, which is 7. The new current underscore area is 7 times 7, or 49, which updates the max underscore area to 49. Here, the height at the right pointer is smaller, so we move it inward to index 7. Now the width is 6, and the height is the smaller of 8 and 3, which is 3. Multiplying these gives a current underscore area of 18, so the max underscore area remains 49. The right pointer is moved inward again, reducing it to 6. Next, the width is 5, and both heights at the pointers are equal at 8. This gives a current underscore area of 5 times 8, or 40. Since 40 is smaller than the current max underscore area, it remains unchanged. The right pointer moves inward to 5. Following this process, the pointers continue moving inward until they meet, and the max underscore area remains 49 throughout. This is our final output for this example. In the second example, the height array contains just 2 elements, both equal to 1. Here, the left pointer starts at index 0, and the right pointer at index 1. The initial max underscore area is 0. We calculate the width, which is 1, and the height, which is the minimum of the 2 heights, also 1. Multiplying these gives a current underscore area of 1, which updates the max underscore area to 1. Since the heights at both pointers are equal, we move the right pointer inward to index 0. At this point, the pointers meet, and the final output is 1, as no larger area can be formed. In the third example, the height array is 4, 3, 2, 1, 4. The left pointer starts at index 0, and the right pointer at index 4, with an initial max underscore area of 0. First, the width is calculated as 4, and the height is the smaller of the 2 heights, which is min, 4, 4, or 4. This gives a current underscore area of 16, which updates the max underscore area to 16. Since the heights at both pointers are equal, we move the right pointer inward to index 3. In the next step, the width is 3, and the height is min, 4, 1, which is 1. The current underscore area is 3 times 1, or 3, so the max underscore area remains 16. The right pointer is moved inward again to index 2. Next, the width is 2, and the height becomes min, 4, 2, which is 2. Multiplying these gives a current underscore area of 4, so the max underscore area remains 16. The right pointer moves inward to index 1. Finally, the width is 1, and the height is min, 4, 3, which is 3. This results in a current underscore area of 3, and the max underscore area is still 16. Once the right pointer moves to index 0, the pointers meet, and we conclude that the final output for this example is 16. The optimized solution to the container with most water problem relies on a 2-pointer approach, which we can now analyze in terms of time complexity. First, initializing the 2 pointers, left and right, along with the max underscore area variable, each takes constant time, or O1. The main computation occurs within a while loop, where the pointers move toward each other until they meet. For an array of length n, the 2 pointers can make at most n1 movements before they converge, meaning this loop runs in O(n) time. Within each iteration, the area calculation involves determining the width between the pointers and the smaller of the 2 heights, both of which are O(1) operations. Similarly, adjusting the pointer corresponding to the shorter height also takes constant time. Finally, when the loop completes, returning the maximum area is another O(1) operation. Altogether, the loop dominates the runtime, making the overall time complexity O(n). When considering space complexity, this solution is extremely efficient. The height list provided as input does not incur additional space usage since it is not duplicated or modified. The algorithm uses only a few auxiliary variables: left, right, max underscore area, and current underscore area. Each of these variables requires constant space, or O(1). Importantly, the two-pointer approach avoids the need for any additional data structures or recursive calls. As a result, the total space complexity of this solution is 1, making it very space efficient. To understand the efficiency of the two-pointer approach, let's compare it to the brute force method. In the naive solution, we calculate the area for every possible pair of indices, I, j, or I less than j. This involves an outer loop that iterates through each starting index I, which takes n time, and an inner loop that iterates through all possible ending indices j for each I, also taking n time in the worst case. The area calculation for each pair is an O1 operation, but since the nested loops evaluate all combinations, the overall time complexity becomes n squared. By contrast, the two-pointer approach eliminates redundant computations by narrowing the search space during each iteration. Instead of evaluating every pair, it strategically moves the pointer at the shorter height, focusing only on the most promising pairs. This optimization reduces the time complexity from n squared to n, while still maintaining the same space complexity of 1. The two-pointer approach demonstrates consistent efficiency in all scenarios, as the time complexity remains n, regardless of the input configuration. This is because the two pointers always meet after at most n1 iterations. The algorithm handles edge cases gracefully, such as arrays with uniform heights, decreasing heights, or random heights. For example, whether the heights are 1, 1, 1, 1, 5, 4, 3, 2, 1, or 1, 8, 6, 2, 5, 4, 8, 3, 7, the number of iterations does not exceed the array length. In summary, the two-pointer approach achieves a time complexity of n by iterating through the array once, and a space complexity of 1 by using only a constant amount of auxiliary space. Compared to the brute force method, which has a time complexity of n squared, the optimized solution is significantly more efficient while maintaining the same minimal space usage. This makes it an ideal choice for solving the problem effectively. When solving the container with most water problem, there are several common pitfalls to watch out for. First, relying on the brute force approach is a major issue. While it's conceptually simple, its n squared time complexity makes it impractical for larger inputs, especially with constraints reaching 10 to the power of 4 or more. Instead, you should always aim for optimized solutions. Second, misunderstanding the problem is another frequent mistake. Ensure you fully grasp whether the goal is to find the maximum area, a specific configuration, or something else entirely. Misinterpreting the requirements can lead to incorrect solutions. Another critical mistake involves the height calculation. Remember that the height of the container is determined by the shorter of the two lines being considered, not the taller one. This is a key part of the formula for calculating the area. Many also struggle with the two-pointer technique, either by moving the wrong pointer or managing both pointers incorrectly, which defeats the purpose of this efficient strategy. Finally, overlooking edge cases can cause your solution to break. Cases like arrays with only two elements, arrays where all heights are equal, or those with a wide range of values should always be tested to ensure your implementation is robust. Now, let's discuss some insights that can prove helpful during interviews. One expectation interviewers often have is that you'll recognize the inefficiency of brute force and quickly propose the two-pointer approach, which reduces the time complexity to n. It's important to clearly articulate your thought process when making this choice. Additionally, be ready to talk about the trade-offs involved. Explain why the two-pointer method is not only optimal but also simplifies the solution compared to others. This shows your understanding of algorithmic efficiency. Another key point is to communicate how you've accounted for edge cases. For instance, how would you handle small arrays with just two elements, arrays where all heights are identical, or inputs with extremely large constraints? This demonstrates thoroughness and attention to detail. Moreover, this problem is a classic example of the two-pointer technique, a pattern that's frequently used in algorithmic problem solving. Interviewers are often evaluating your ability to recognize and apply such patterns to other scenarios. To further your preparation, consider exploring related problems like LeetCode 42, trapping rainwater, which also relies on calculating areas with heights, or LeetCode 15 and 16, which involve two-pointer logic in sorted arrays. Each of these problems reinforces the concepts used in this one. Finally, let's explore alternative approaches and their trade-offs. The brute force approach involves calculating the area for all possible pairs of lines. While it's straightforward to implement, the O(n²) time complexity makes it highly inefficient for larger inputs. The trade-off here is simplicity versus performance. On the other hand, the two-pointer approach is far more efficient, with a time complexity of O(n). By starting with pointers at both ends of the array and moving the one corresponding to the shorter line inward, you systematically search for the maximum area. The key intuition behind this technique lies in prioritizing the possibility of increasing the area. While it's efficient, it does require a solid understanding of why and how the shorter pointer is moved. A less common alternative is the divide and conquer method, which involves breaking the array into smaller subproblems and computing areas recursively. However, this approach is more complex and doesn't offer significant performance advantages over the two-pointer technique. As such, it's rarely used in practice for this problem. When choosing an approach, always weigh the clarity of implementation against the efficiency required for the given constraints. Great job! Today, we unraveled the number 11 container with most water problem, applying the efficient two-pointer technique to optimize our solution. Remember, practicing problems like this sharpens your algorithmic thinking and prepares you for real-world scenarios. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding insights. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!